Kaur is again in front of you to discuss some new concepts of group theory. In previous lecture, we had discussed two theorems, very useful and important results on order of elements in a group. Now we proceed further with a new result. Let A, B and X be any elements of group G. A, B and X are any elements of the group. Then what we have to prove? First result is order of A inverse is equal to order of A. That means if we know the order of A, then order of the inverse of that element is also same. We need not to find the order of inverse element again. Now here is the proof. Let order of A is equal to M and order of A inverse is equal to N. We have renamed it as M and renamed it as N. Now what we have to prove? We have to prove that M is equal to N. Now again, to prove that M is equal to N, we shall prove that M divides N and N divides M. If M and N, both numbers divide each other, then clearly M should be equal to N. Now, let A inverse raised to the power M is equal to, now from where we have to start? We know that order of A inverse is equal to N. So we shall start with A inverse raised to the power M. And again, as we know that order of A is equal to M, so we shall start with A raised to the power N. We have to do the reverse. Now, A inverse raised to the power M is equal to, it can be written as A raised to the power minus M. Now, this can be written as A raised to the power M raised to the power minus 1. Now, what is M? M is the order of A. That means it must satisfy that A raised to the power M is equal to identity, and we know that since M is the order of A, so M is the least positive integer which satisfies this property. Now substitute A raised to the power M is equal to identity here. We have E raised to the power minus 1 and inverse of identity is inverse. So we get identity. Now we have A inverse raised to the power M is equal to identity. And we know that what is the order of A inverse? N. And any other number which satisfies this property, then this order N must divide this power M. So that means N divides M. Let's mark it first. Again, A raised to the power N can be written like this. Again, minus N can be split into N into minus 1. Now order of A inverse is N. So order of A inverse is N, that means A inverse raised to the power N should be equal to identity. Now identity raised to the power minus 1, that is inverse of identity, that is equal to identity. But order of A is equal to M and A raised to the power N comes to be identity. We know that any other element which satisfies this type of property, then order of the element must divide this power. So that means if order of A is equal to M and we have A raised to the power N is equal to identity, then we must have M divides N. Now mark it second. From first and second we have M is equal to N. And for first M and N, order of A and A inverse. That means order of A inverse is equal to order of A. Now next result is x inverse Ax raised to the power k is equal to x inverse A raised to the power kx. That means if we take this power k inside, it will be operated on k only. That means power will come to directly A for k is equal to 1. Now we shall prove this result using mathematical induction. Now by using mathematical induction, what we have to do is, firstly we shall prove that this result is true for k is equal to 1. Then we shall assume this result is true for k is equal to m, and then we shall prove that this result is true for k is equal to m plus 1. If we are successful in proving all this, then we can say that this result is true for every positive integer. Now let's start
mathematical induction. For k is equal to 1. Now substitute 1 here, substitute 1 here. What you get? X inverse ax raised to the power 1 is equal to x inverse a is power 1x. That is same. That means result is true for k is equal to 1. Now let the result holds for k is equal to m. Let us suppose that the result is true for k is equal to m, where m is any positive integer. If this result is true for k is equal to m, then x inverse ax raised to the power m should be equal to x inverse a raised to the power m x. So let us suppose that this is true. Now we have to prove this result for m is equal to m plus 1. Now we shall start with here m plus 1. X inverse ax raised to the power m plus 1. Now m plus 1 we can split it. Raised to the power m raised to the power 1. Now here x inverse ax raised to the power m. As we have already assumed that result is true for k is equal to m, therefore we can apply that result here. So apply it here, x inverse a raised to the power m x, and take it as it is. Now using associativity we can collect these two elements because these all are in multiplication. So collect these two elements, x into x inverse, any element operated with its inverse we get identity. So here we have identity, and any element multiplied by identity we will get the same element again. So e into ax is ax. So what we have? We have x inverse a raised to the power m ax. Now collect these two powers, a raised to the power m into a raised to the power 1, that is a raised to the power m plus 1. So what we have proved? We have proved that x inverse ax raised to the power m plus 1 is equal to x inverse a raised to the power m plus 1x. That is, this result is true for m plus 1. Hence, the mathematical induction is over. We are successful in applying mathematical induction. So this result is true for every positive integer. Now we shall prove this result for k is equal to 0 and for k is equal to some negative integer. Also for k is equal to 0. Now put k is equal to 0. Anything raised to the power 0 is identity. Now I can write identity like this also, right? Because ex is x, x inverse into x is identity. So I can write identity as x inverse ex. Now e can be written as identity, e can be written as a raised to the power 0. So we can write x inverse a raised to the power 0 x, which is equal to the right hand side. So for k is equal to 0 also the result is satisfied. Now we shall check this for negative integer. Now let k is equal to minus m, where m is some positive integer. If m is positive, obviously minus m is negative. So we are proving this result for some negative integer whether it holds or not. Therefore x inverse ax raised to the power k is equal to, substitute the value of k, that is equal to minus m. Substitute minus m here. We have separated m into minus 1. So this, here is m, here is minus 1. Now m is positive integer, and we have already proved that this result is true for every positive integer. We have proved this using mathematical induction. So we can apply it here also. You can write x inverse a raised to the power mx inverse. Now distributing this inverse inside, what you get? X inverse a minus m, that is a raised to the power minus m, and here you will get x inverse inverse, and we know that inverse of a inverse is equal to a. We have already discussed this. So that means inverse of x inverse will be equal to x, right? So we have arrived at x inverse axk, where k is equal to minus m here, is equal to x inverse a raised to the power minus m x. So this result is also true for negative integers. That means for every integer, whether the integer is positive, whether negative, whether 0, this result will hold. Now next result is order of a is equal to order of x inverse ax. we have to prove this. Order of A is equal to order of x inverse Ax. Let's suppose that order of x inverse Ax is m and order of A is equal to n. Again, to show that m is equal to n, what we shall do? We shall prove that m divides n and n divides m. Because if both numbers divide each other, then we must have m is equal to n. Now let's start. X inverse Ax raised to the power n. Same as here, as I have told you, that if order of this is m, we have to start with taking power n. If order is n, then start taking with power m. Now let's start. X inverse Ax raised to the power n. We have proved that according to this result, we can write it as x inverse a the nx. According to this second part, now x inverse a raised to the power nx. And we know that order of a is equal to n. And since order of a is equal to n, you can write a raised to the power n is equal to identity. And identity into x is x inverse into x is identity. Right? We have arrived that x inverse Ax raised to the power n is equal to identity. But order of this element is m. And we know that any other element which satisfies this property, that power should be divided by the order of that element. That means this m, this order of this element must divide this number n. So this implies m divides n. Let's mark it first. Again, since order of x inverse Ax we have already assumed m. Now you can write x inverse Ax raised to the power m is equal to identity according to the definition of the order. Again, using second part, you can write a raised to the power m here in next step. Now e can be written as x inverse into x also. And in next step, you can write x as ex. Now compare these two elements which are equal. As we have already studied, left cancellation law as well as right cancellation law holds in groups. Now again, you can apply these cancellation laws here. Cancelling x inverse from left side, cancelling x from right side, that is left cancellation law, that is right cancellation law. You will get a raised to the power m is equal to identity. That is a the m is equal to identity. Again, come to that point, order of a is equal to n. That means if this property is satisfied by any other number other than order of the number, then order of that element must divide this number. That means n must divide m. Mark it second. From first and second, we can say that m is equal to n. What was m and n? M and n was order of x inverse Ax and order of A. That means order of these two elements is equal. Now from this result, we can derive a very useful result, that is order of AB is equal to order of BA. Very easy. What we have to do, just replace A by AB. Replace A by AB. We get order of AB is equal to order of x, replace x by A. Because this is true for all elements of the group. A, x, they can be any elements of the group. And here in particular, we are replacing A by AB and x by A. That means here A element is AB and here x element is A. So what we get, see here, x is A. We have replaced A by AB and x is again A. Now what is A inverse into A? This is identity. You can write identity here and identity into any element that is equal to that element. So where we have arrived? We have arrived at order of AB is equal to order of BA. That is the result we want to prove. Thank you.